Circle geometry, starting with the chord theorems. Let's have a look at the parts of the circle first. There we have the arcs. That's a chord cutting across the circle. Radius we know, diameter we know, and there is the tangent touching the circle. The chords divide circles into segments. And there is a sector, we don't often use it, but the sector is like a slice of cake. Now we have two main chord theorems. First says that the line joining the center of the circle to the midpoint of the chord, so that's the center, the midpoint of the chord is perpendicular to the chord. So it goes midpoint, therefore perpendicular. Then there's a converse. And a converse is a situation, object, or statement that is the reverse of another. So if one statement says, if this, then that, the converse says, if that, then this. In geometry, most theorems have converses, but they are not all necessarily true. This one is, midpoint means perpendicular, and the converse would say perpendicular equals midpoint. Well, if we draw a perpendicular from the center to a chord, it does bisect the chord. Therefore, there's the theorem. A perpendicular from the center of a circle to a chord bisects the chord. And we refer to these as the chord theorems. Let's look at an example. We use a lot of Pythagoras' theorem in these ones because it's quite a bit in terms of right-angled triangles. So given 16, given that's bisected, means we can find the value of SP very easily. If we're going to use right-angled triangles, we need to draw radii in at times. Why is OP perpendicular to ST? A chord theorem. And why is that the case? Well, it's Pythagoras' theorem. And therefore OS is 10. Now this is a case of a well-known Pythagorean triple. Pythagorean triples are certain well-known numbers which form right-angled triangles. Like this is a 3, 4, 5 triangle, though in this case it's 6, 8, 10. Double 3, double 4, double 5. But you need to be aware of the 3, 4, 5 triangle, but remember the 5 must be the hypotenuse opposite the angle. It could be 3, 4, 5, 6, 8, 10, 30, 40, 50, many different variations on it, as long as they're all multiples of the 3, 4, and 5. There's also a 5, 12, 13, and there's a 7, 24, 25, many others. In this case, calculate that distance there. So that's perpendicular, and SP equals PT, reason, chord theorem. So therefore we know that's 6. Now if we have a look, I say, well, is it a triple? No, because that's 6, 9. If we divide it by 3, that's 2, 3. No. So we'll use Pythagoras' theorem. Not going to work out as a very nice number. But there we are. Your calculator will give the same. A mixed surd, 3 root 5. Now in this case it says calculate the distance between the parallel chords. Well, the distance between two parallel lines is a perpendicular line drawn between them. For convenience sake, we're going to draw it through the center, which makes it very useful. Because it's perpendicular to that chord and perpendicular to that chord, it means it bisects both chords. Now, OL is 5. Why is that? Of course, OL is a radius. Now we have two right-angled triangles. We need to find the distance from M to P, so we find this distance OP, that distance OM, and we add them. So working in this triangle here, OSP. Well, that's a 4. The hypotenuse is a 5. Therefore, by Pythagoras' theorem, that has to end up being a 3. Let's go through the motions. There we are, 3. Now, if we look at this one, 5, hypotenuse, 3, one side. The other side must be 4. Very useful word in math, similarly, abbreviated to simile. We can only use it if it's by exactly the same steps, same reasons, everything, just in a different part of the figure. So adding together we have 7. Find the value of x. SP equals PT. Notice both 6. What does that mean? Yes, a right angle. Reason being chord theorem. Now, complete. OQ equals what? Hopefully you see it. OQ is equal to OS, which is x. The reason being they are both radii. So therefore we can now find the length of OP in terms of x. There's x, that's 3, therefore x minus 3. We have a right angled triangle, we can form an equation. Pythagoras theorem. That squared, hypotenuse squared, equals that squared plus that squared. Now we simplify and solve the equation. And we have that x is 7.5 centimeters. Right, in this case, we need to find the value of x there. In order to be able to link the chords to the circle, we need to draw a couple of lines in. And what would they be? They would be the perpendiculars. AB equals, not a trick question, 12, eh? 3 plus 9. Therefore, what's AP equal to? Remember, this is a perpendicular. Therefore, AP is 6. The reason being chord theorem. Which means we can give the length of KP now. Because we know that's 3, so KP is what's left, the other 3. Of course, KP is equal to another line in the figure. And that is OQ. Why is that? Because this is a rectangle and the opposite sides of rectangles are equal. Now let's find KQ. KQ we can find it exactly the same way as KP. It's like that similarly set up. KQ is 5. Have a look. 2 and 12, 14. Halved is 7, and that's 2. So the remainder is 5. Now let's take that triangle situation. We've taken just the highlighted blue triangle. There it is there. And we don't have a 3, 4, 5 triangle. Why not? Because the hypotenuse is x. That is not the hypotenuse, that's 5. So we need to use Pythagoras' theorem. Solving, not a very nice number, but there you are. X equals the square root of 34, which is 5, 8, 3. Strictly speaking, in this one, of course, you'll see that it works out as impossible, but have a look and see for yourself why. This next one, calculate PM. Well, PM just by Pythagoras' theorem, it's a 3, 4, 5 triangle. PQ, PQ is double PM, chord theorem. OP is 100 divided by 2, 50, because that's the diameter, and we have another right angle triangle, and it's a 3, 4, 5 again. So TP is 30, so therefore QP, because this is perpendicular, TP and QT must be equal, so QP is twice 30, 60 millimeters. Number 3. O is the center of the circle, M is the midpoint of AC. OM 20, AC 40. Calculate the length of AB. We want the diameter, in other words, we must find the radius first. That's a right angle. Reason being, center to the midpoint. So we know that's 20, just half of 40. Now we use Pythagoras theorem, and we end up with AO equaling 20 root 2. So to find AB, we just double it. We get 40 root 2. In number 4, we also have a right angle. So now we have a 40 there because it's the midpoint. If we draw in the radius, we can find the radius of the circle by Pythagoras theorem. So it gives you 40 root 2, and we're going to double it to get the diameter, 80 root 2. Calculate the radius of the circle. Well, we can get it from this part, and hence the length of CD. Well, once we know the radius, we can go into this part. So that's half, 30. Reason being chord theorem. Now we have a 3, 4, 5 triangle, therefore the radius is 50. Notice I've drawn that in 2 to show it. Now we have another 3, 4, 5 triangle on this side, right angle triangle, 40. Therefore CD is 80. Number 6. Length of OM. Well, we know that that's a perpendicular, therefore we know that that is half. And we're going to have to let the radius or OM be x. There we are. Better to let OM be x because that is the length we're trying to find. Now, if we draw an OB, we know the length of the radius because OC is also a radius. So therefore, OB is x plus 1. We can use Pythagoras theorem for an equation. And solving the equation, we get x equal to 4 millimeters. In other words, that's the length of OM, 4 millimeters. Finding the distance between the parallel chords. Remember, we need to draw on the perpendicular between them. There we are. Here's, we're going to add two distances. Here we're going to subtract that distance minus that distance. There we are. How do we know the 50? Because we're told it. OK1 is 40. OK2 is 30. Same here. OK1 is 40. And OK2 is 30. Just by 3, 4, 5 triangles again. So K1, K2, that one is 70. And K1, K2 there is 10 millimeters. Distance between the parallel chords, same sort of thing. Drawn the lines, and we now have 5, 12, 13 triangles. Notice 5 something 13, 12 something 13. It's a 5, 12, 13, but you can do the full Pythagoras theorem and you'll find that K1, K2 ends up being 17 in this case, because that's 12, that's 5. In this case, that's 12, that's 5, so we subtract and we get 7. Two concentric circles, radius 17, radius 10, and we have to find the length of BC. Well, we can use this one to find the length of AD, which we know, so therefore we can find that distance there. There we are. So I've drawn in a perpendicular, OK, because once I know that length and know that radius, I can find KC. So there we are. There's another Pythagorean triple. 8, 15, 17. Now we have 8, we have 10. Well, that's 2 4s, 2 5s, therefore 2 3s. So KC ends up being 6. And because this is a perpendicular, it's bisecting BC, so the whole of BC is double, which is 12. Bit of a toughie to end. 2 circles pass through the center. This circle passing through that point, the other circle pass through that point, and those are the centers. It actually means the 2 circles have equal radii. They must do. Determine the length of the common chord there. So I'm going to draw a perpendicular in. MN is also equal to R, because it's a radius of either circle. So ON is R over 2. Because this is a kite or rhombus, these must intersect at right angles. So now I can say AO squared equals R squared minus ON squared. It gives me an equation with R. So therefore AO is root 3 over 2 times R. Square root of that. And that gives me AB is twice that length, so therefore we have AB is root 3R. Let's have a brief look at the actual theorem proofs. We're going to use congruent triangles. So, given. Notice we only use given in a theorem or theorem proof if it cannot be shown in a figure. I would not say given AN equals NB because I can show it on the figure. But we cannot show in the figure that O is the center, so I put given O center. Required to prove ON perpendicular to AB. Construction. We need to join the 2 radii. So now we're going to prove those 2 triangles congruent. That's simple enough because AN equals NB, the reason being given. OA equals OB, the reason they are radii. And ON is common. So we have these 2 triangles congruent, and we must put the case for congruency. I've stated them in the correct order, and the case for congruency is side, side, side. Therefore, that angle equals that angle. But they add up to 180. Therefore, they are 90, and it's proven. Chord theorem. Let's have a look at the converse one. And we're going to say, do it yourself. Let's try it. Try it yourself. So pause and try to prove this theorem using the template there. Given the same thing, that O is center. Required to prove? Well, we required to prove that this perpendicular bisects the chord, and with required to prove, we always interpret it in terms of the actual diagram. So I would not say required to prove the perpendicular from the center to the chord bisects the chord. I would just say AN equals NB. Yeah. Construction, well, we're going to draw in the radii. Now the proof in triangles. Well, they're the 2 triangles. N1 is equal to N2, and they're 90 degrees. And the reason is given. OA is equal to OB, because they're radii. And of course, ON is common. Therefore, triangle OAN is congruent to triangle OBN. And our case for congruency, well, have a look. We have at 90 degrees, we have those equal, and we have that equal. Don't make the mistake. In fact, this is the case. Sorry, I was going to make the mistake of thinking it's right angle hypotenuse side, but in fact, in this case, it is. Because you see, we have side there, angle here, and side there. So it's two sides in the non-included angle, which we cannot use unless it is the special case of right angle hypotenuse side, which it is, and therefore we say RHS. Therefore, and straight away we could say, well, AN equals BN, or AN equals NB. And we will just say reference chord theorem as well.